Okay, so welcome to lecture 4. So in this lecture we are gonna talk about the DFS algorithm or depth first search algorithm. So before we dive into the lecture, let's talk about what we have covered so far in the lecture 1, lecture 2 and lecture 3. So in the lecture 1 we started with the AI definition and talked about the agents in AI. Then in the lecture 2 we talked about how to model AI problem as search problem. Then we talked about what are the components needed like initial state space graph, actions, transition model, path cost function, etc. Then in the lecture 3 we talked about BFS search algorithm. So how does BFS work? We talked about the concept of frontiers or and also we talked about visited set and so on. Apart from that, we also talked about how to compare two algorithms, right? To search algos. So for for that we talked about what branching factor is, what a right, what branching factor is, what the D is the depth of shallowest node, and what is the M, which is the longest path in the state space graph. And apart from this, we also talk about the notion of completeness, notion of optimality, and so on. So we talk about these things till the lecture 3. So let's talk about now in this lecture we are going to talk about another search algorithm called DFS or DFS stands for the depth first search. This is another very common algorithm that you must have studied in your different courses like data structures or algorithms. तो this algorithm also जो आपने इन दोनों कोर्सेज में डेटा के कोर्स में या फिर एल्गोरिथम्स के कोर्स में ऑलरेडी पढ़ा होगा even if you haven't like studied this algorithm before we'll go over in a pretty much details की exactly क्या हो रहा है and so before we go into the depth first search let's talk about or let's revise our approach that we have discussed in the last lecture or in the lecture 2. So we defined a general search strategy or some general search approach which starts with the key frontier containing the initial state. So this frontier we also called this frontier as an open list. And so we start with the frontier containing our initial state. And so depending upon how we implement this frontier, we'll come up with various algorithms. So for example, अगर मैं इस frontier को I implement this frontier using a queue. Then we talked about BFS. But if I simply implement this as a stack data structure, then our DFS will be generated. So one thing that you need to know about the DFS is that it uses the stack as a frontier. Then, what's the general search strategy? We start with the frontier, which contains the initial state. After that, we also maintain an explore set on the closed list, which is initially empty. What is the purpose of this? It's to store all the states which has been explored or visited. So we'll start with these two data structures. One frontier which contains the initial state and another empty explored set which initially is empty and we'll keep adding nodes which we are exploring into this explored set. So what we'll do? We'll loop over the loop. We'll run a loop which will first what are the different steps in this loop? We'll first check whether frontier is empty. If frontier is empty, that means that there are no new nodes or no states which need to be explored. That means that we haven't found the solution yet, or we haven't found the goal node yet, and also we don't have any other nodes to explore or any other nodes to visit. That means we have exhausted our search. That means we have to return no solution. We haven't found any solution. We haven't or found any solution. If if it is not empty, then we'll remove one node from the frontier. So this removal of the node की कौन से node को remove करना है frontier में से, this will depend upon the how frontier is implemented. For example, queue में क्या होता था कि queue में जो element first insert हुआ है queue में, that will be the first one to be taken out of the frontier. But in stack, we'll see that the stack works quite differently from the queue. In stack, element which is being pushed at the end of the or at the last or which will be first one to taken out of the stack. So we'll remove the a node from the frontier. We'll check whether node is a goal node or not. If it is a goal node, that means we have found our goal. We will return the solution. What is solution? It's a path path from initial state to goal state. Okay. If this will terminate the algorithm, so this return statement will always terminate. As you know, you can define this algorithm as a function, so the return statement will always be the end of that function. But if the node is not a goal node, then what we'll do? We'll add the node to the explode set. So we'll mark it. Adding it to the explode set means that marking it as a visited set. Visited key, we have explored this node and we don't want to come to this node again in the future. And we'll expand the node. So what do you mean by expanding? We'll simply generate all the successors of the node. So this is node and इसके जो भी successors है, for example S1, S2, Sn, we'll check whether if these are in the frontier or not. If these are not in either frontier and the explode set, they aren't in the frontier and explode set, then we'll add those to the frontier. So this was our general search approach that we have discussed. So let's talk about how DFS works. So DFS will also have the same approach, but now in DFS we'll use the stack as a frontier for us. So what is a stack? So let's first talk about the stacks and then we'll talk about the DFS itself. So so what is stack? You must have known about a stack data structure है क्या? तो stack is also known as a last in first out data structure. So what do you mean by this? कि in element which is inserted at the last will be first one to removed from the frontier. So this is the element inserted at the last will be the first one to taken out or removed. So how does this stack work? So stack को you can think of stack as like a stack of plates, stack of boxes are also. तो इसमें क्या होता है जैसे suppose you have a stack of plates. So which plate will you choose? Which which is there at the top, right? Because if you remove something from between, then there is a high chance of you breaking the plates and all. So stack can so you can think of stack as a data structure which can be maintained like this. So visually stack is represented something like this. So this is a stack. So for example, if I define some set of operations, for example, let's suppose key we have the operations add one, what it will do, or if I let simply so push one. In case of stack, we use the terminology push and pop. So push one means कि we'll add one to this top of the stack, so it will be one. If I have another operation called push two, it will add two at the top of the stack, and another operation like push four, so it will add four at the top of the stack. But now let's suppose I have an operation called pop. So what this pop operation will do, it will remove the element from the top of the stack. So which element is at the top? 4, so it will be removed and it will be returned. So it will return 4. Now, if I have another element called push 5, so it will be push the 5 at the top of the stack. And if I again remove, so what is the top element here? 5, so it will remove 5. And if I have another pop, let's suppose what it will do, now which is the top 2, so it will return 2. And if I keep continuing pop, what it will do, it will remove 1 from the stack. And if I do pop again, so then stack is empty, right? Empty. So it will return error or something like exception or anything how you implement depending upon your exact implementation. But this will not be a valid operation, right? Since the stack is empty. So this is how stack works, and the one of the cool thing about stack is the operations like push and pop. These are order one operations, like they take constant amount of time. So stack can be implemented either using arrays, we can implement arrays or linked list, etc. We will not talk about the exact implementation of the stack and queues. So I hope that you already know about these from your data structure course or from your algorithms course. If not, then it's a very simple implementation. You guys can go over some videos of how to implement a stack using arrays or using linked lists. So that's up to you. You can search over the internet and find out about this. It's a very simple data structure, not that much of a complexity involved in this. So let's not go into the implementation data since this is not a course on data structures or algorithms. We're talking about AI. So here we are using stack just as a data structure, and we are using the functionality of stack to implement our DFS algorithm. So now that we know this frontier is implemented as a stack, now let's see how. So other than this, all entire algorithm is just same. Let's see an example of let's see an example how DFS works over it. So let's again visit back to our example. So in the last lecture we solved this example using BFS. Now let's solve this using a DFS and how this works and so. Okay, so now our this frontier This is a stack frontier. That means ki any element which is being pushed at the end will be the first one to be removed from the frontier. And there is this explore set, or we can set it as a visited set. So anything which has been added into the explode set, we treat as if this node has been explored and we don't want to visit that node again in the future. So this is just to make sure keep our algorithm doesn't go back and forth between two states only, right? Remember, we, we saw an example of key if this is the edge and there was no export set, then our algorithm was keep circling between these two states. So this is why the export set is made. Okay, so let's run our DFS algorithm. Okay. So what's the general strategy? We'll start with the frontier containing the initial state. So this is our initial state, and this is our goal state. Okay, so let's insert the initial state into the frontier. So this is our starting of the algorithm. Now what we'll do, we'll check whether the stack is or the frontier is empty or not. Is it empty? No, because there is one node into the frontier. So since it is not empty, we'll not return key, there is no solution. Instead, what we'll do, we'll remove the node from the frontier. So let's remove the node from the frontier. So I'm crossing it. That means we have removed this node from the frontier. And let's set a temp variable which kind of holds this value or the temp node for the temporary observation, because we need to explore this, right? We need to generate all the successors of this and add those back to the frontier. So now we have removed this and we'll check whether it is a goal node or not. So if temp is equal to e, what we'll do? Return solution, because we have found the goal node. Else add neighbors to frontier, right? This was our, so since A is not a goal node, A is not E, so let's add the neighbors of A into the frontier. So what are the neighbors of A? We can simply generate all the neighbors using transition model. So A के neighbors क्या? Only B. So we'll check whether B is in the explode set. No, B is not in the explode set. So before, while we are exploring A, we'll add this A into the our explode set, ताकि we don't go back to this. So B is not in the explode set and B is not in the frontier either. What we'll do, we'll simply add B into the frontier and we'll continue with our algorithm. We'll again check whether frontier is empty or not. Frontier is not empty, right? Because B is there, so we'll remove the node. Let's remove B. We have removed B. So now this temp adds the B. Is it equal to E? Then if it is equal to E, then we'll return the solution. If not, then what we'll do, we'll simply mark it as a mark B visited and we'll explore the B. So what we'll do, so we will explore the B. The B के जो भी successors है, which are C and D. We'll check whether these are in frontier or not, or in explore set or not. C, it is not in the explore set, so we'll insert C. Let's insert C and we'll check whether D is also not in the frontier, so let's insert D. Now again we'll keep continue with our approach. We will remove a node from the frontier. Now, see, there are two options. See, which node to remove. तो जैसे BFS में क्या हो रहा था? We were using Q as a frontier, तो we are removing the node which was inserted first. तो यहाँ पे insert पहले क्या हुआ? C, then insert हुआ D. But in stack, we remove the node which is been inserted later. So हम कौन सा remove करेंगे? We'll remove D since it has been inserted later than. तो technically हमने यहाँ पे साथ में insert किया है, तो you can also insert D and C. But let's go into the alphabetical order and insert C first, then D. So we'll remove D. Is D equal to E? No, D is not equal to E. So we'll explore the D. We'll mark it as explode set and we'll generate the successors of D. Right? So what are the successors of D? F only. We'll check whether F is in the explode set or the frontier. It is not in the explode set and not in the frontier. So what we'll do? We'll add F into the frontier. Again, we'll continue with our approach. What we'll do? Remove the node which has been inserted at the last. तो अभी कौन सा insert हुआ? F. Remove F. F remover. F is not equal to E. That means E. We can explore F. So we'll add it to the explore set and we'll add F k neighbors. So F doesn't have any neighbors, right? That means keep no new node is generated now. So we'll not insert anything into the frontier. So what we'll do, we'll again check the frontier. We'll check whether frontier is empty or not. Frontier is not empty because C is still there. So what we'll do, we'll remove the C. We'll remove the C. Check whether is it equal to goal node. Is it goal node? No, it's not a goal node. So we'll explore the C. Add it to the frontier and then what? We'll explore all the neighbors of C. So C का कौन सा neighbor है? E, right? C only has E, neighbor E. So we'll check and insert that into the frontier. So let's insert E into the frontier. Now what we'll do? We'll again check into the frontier whether it is empty or not. It is not empty. There is E. We'll remove E. Is it equal to the goal node? Yes, it is equal to the goal node. So what we'll do? We'll return the solution. So that's it. And what will be the solution? Solution will be the path from initial state to the goal state. So what is the solution here? The solution here is A, B, C, and E. So this is our solution. Okay. So this solution can also be found using this tree I have generated. This is called DFS tree. So that's how DFS works. Okay. So let's go over this algorithm in for one more example. One popular example that we are discussing for the Romania's, right, where agent wants to travel from CTRR, which is our initial state, to city Bucharest, which is our goal state. Okay, so let's run our DFS algorithm for this. So let's maintain a frontier. So let me use this space. Right. Sorry about this, since I don't have the large space here. I'll use this as a stack frontier, and this as a visited set, visited set or explored set. Okay, and this is where we'll draw our search tree. Okay. Sorry about the congestion space, just bear with. Okay, so what the our strategy will start with the initial state being in the frontier. So we'll add initial state A as a frontier in the frontier. So we are again I'm using just the first letter of the city names. So this is our initial state being in the frontier. Now what we'll do, we'll simply remove the node from the frontier. So let's remove the node. Let's remove A. What we'll do, check whether this is a goal node or not. Is A is goal node? No, because goal node is our B. So what we'll do, we'll simply add it to different visited set, and so we'll also insert it in the different search tree. And since we have added it to this visited set, what now we'll do, we'll all add all the successors of the A into the frontier. So what are the successors of A? A has three successors: S, T, and Z. So let's add all these into the frontier. So S, T, Z. Now we'll simply repeat our process. What we'll do, let's again remove a node. Which node will be removed? Which is at the top. So Z will be removed. Is Z equal to the goal node? No, because goal node is B. So we'll insert into the visited set. And since this Z is being visited from the A, we'll add it to the search tree also with a neighbor of A. Now what? Z will again do the exploration of Z. Z के क्या neighbors है? Z has neighbor O and another neighbor A, but we realize कि A तो already visited है or already explored है, so we'll only add O into the frontier. So let's all add O into the frontier. Now what we'll do? We'll again follow the same strategy. Remove A. Is it a goal node? No, it's not a goal node. So we'll mark O as a O in the O as a, in the explode set and add it to the frontier or search tree. Now what? O क्या neighbors? O only has one neighbor called as CVU, but we realize that CVU is already in the frontier. It is not explored yet, but it is already in the frontier. So our general strategy was we'll not aim anything as long as this is in the front. This is already in the frontier और एक्सप्लोर सेट अगर इन दोनों में से किसी एक में भी है तो विल नोड ऐड दिस नोड इनटू द फ्रंटियर बिकॉज वो ऑलरेडी फ्रंटियर में तो वो ऑलरेडी एक्सप्लोर हो जाएगा व्हाई डू वी नीड टू ऐड दिस अगेन इनटू द फ्रंटियर so since there is no other successors of the O we will not add anything into the so now what we'll do we'll simply choose the node which is next in the frontier which is T. We'll remove T, mark T as a visited. Okay, since T is not a goal node, we'll add the successors of the T. और सिर्फ P किसके थ्रू एक्सप्लोर हुआ है, A के थ्रू, तो विल ऐड insert A into the or add T in as a child of this A in search tree. तो P के successors क्या है, T के successors are 2 A and L, but A is already explored or already marked explored, so we'll not add A into the frontier, but we'll add L into the frontier. So let's add L into the frontier. Now what? Just pick a node again. Which node will you pick again? L, because it is in the top of the stack. Mark L as a visited, और L किसके थ्रू एक्सप्लोर हुआ है, T के थ्रू, तो let's add L to the add L as a child of T in the search tree, and उसके साथ साथ since L is not a goal state, or so we'll add all the successors of L. So all the successors of L are M and T, but T is already marked visited, so we'll not add T into the frontier. So we'll add M into the frontier. So let's add M into the frontier. Again, we'll continue with our algorithm. Remove M since it's at the top of the stack. Mark it visited, and since M किसके through explore हुआ है, L के through, add into the search space, search tree as a child of L, and M के जो भी successors है, which are D and L, but L already explored है, तो only D will be added into the frontier. So add D into the frontier. Now what? Again repeat the process. Remove D. Mark it as a visited. Is it a goal node? No. तो जो भी अगर goal node नहीं है तो what will do? Add D into frontier. Sorry, and search tree also. And D के जो भी neighbors है, which is C, will add C into the frontier. So let's add C into the frontier. Now realize this fact. What DFS is doing? Why is the name DFS itself? So what DFS did, if I just explore the or observe the DFS, how DFS was working. So DFS did first it picked this path, then went along this path until there was no any other path left, right? Because S next path was S, but also S was already visited. So it went along this path unless there was no next path left. So after what it did, it chose another path. Now it chose this path and it's going this path along this path until we reach somewhere where this path ends. But अभी इस path पे और भी है, तो now it has to choose either this way or either this way, right? So it will choose one and again go along with this path जहाँ पे end हो जाए. So this is how the algorithm is working. Okay? It is just picking one path and going along this path until we reach the end of that path. So this is why this name depth first search. This picks one side of one path and goes along the depth of that path as long as this path is reachable or as long as the path is there. And जैसे path खत्म होता है, then it will backtrack and then choose the another path. So what will happen when it is at the C? It will have two successors. Right. Now what we'll do? We'll simply remove C, mark it as a visited, and C किसके through explore हुआ है? D के through. So we'll add it to the. Now C has two successors, P and R. Right. So let's add in those into the frontier. So let's add P. Let's add R. What will happen? We'll again choose the one node. And let's remove R. तो R is not a goal node, तो we'll add into the explore set. And R किसके थ्रू एक्सप्लोर हुआ? C के थ्रू, तो we'll add R as a child of C. Now what? R के कौन कौन से नेबर्स है? R has two neighbors, S and P and C. But as you realize कि S is already in the frontier. As you can see, S is already in frontier, P is already in the frontier, and C is being marked visited. That means if no neighbors of R have, can be added into the frontier. So this is what our algorithm did. It went along this path. यहाँ पे दो options थे. It chose this option and यहाँ पे आ गए. Now it algorithm has realized कि यहाँ से there is no option left. ये option भी खराब है, ये option भी नहीं है. तो यहाँ पे algorithm has found path end. So what it will do, it will now again go back to the previous node जहाँ पे path के options थे. It will get back to here and यहाँ से जो दूसरा option था, it will choose this one. So now it will go to the another step. So what we'll do now, again remove the next node, which is the P. Explore set, mark it to the P, and since P was explored through C, now we'll branch from here, right? And P के जो भी neighbors है, P के neighbors क्या क्या है? There is one neighbor R, but R is already visited, so we'll not add it to it. And another neighbor is B, so we'll add B into the frontier. Now we'll simply repeat our process. What we'll do, we'll remove B, and जैसे B remove करते हैं, we realize कि B is the goal node. So this is the goal node. That means we have found our solution. That means we have found the solution, and so that it will terminate the algorithm. Okay? So this is where the जैसे हमें goal node मिला, we will terminate the algorithm. And ये goal node किसके through मिला? P के through के, तो we'll add here, and B को भी we can mark visited or not. That's up to you. And since we have found the solution, this is our solution for goal node. Now we'll simply return the solution, and so if we return solution, what will be the solution? Solution will be simply this was our initial state. तो initial state से goal node तक का जो path है search tree में, that is our solution. This path. तो जो path हम choose कर रहे हैं यहाँ से, this path is the solution. तो we can simply say कि solution क्या है? A T L M D C P B. This is our path. You can simply return it as a sequence of actions also. And अगर कोई ये पूछे कि किस order में nodes explore हो रहे हैं, तो this our visited set represents the order of nodes in which they are being explored. Okay, so this is how, and you realize that कि BFS ने कौन सा path find किया था? BFS found the path this one. So this was the path that BFS found. And DFS ने कौन सा path find किया? which is much longer than this. This was the DFS. So this DFS found the path which is much longer compared to the DFS. So if we talk about the properties of both BFS and DFS, so we talk in the last lecture we defined some properties. What were those properties? So let's talk about them one by one. So first property that we defined is completeness. तो is it DFS complete? तो completeness क्या था कि अगर आपका सर्च स्पेस में कोई सॉल्यूशन एग्जिस्ट करता है तो whether your algorithm gives that solution or finds the solution, that was the completeness of it. And so is it DFS complete? So technically yes, DFS is complete because it will find the solution, but only if m is finite. What do I mean by this? M क्या था? M was the length of longest path in search tree. और भी टॉप और या फिर हमने जैसे दिखाया था कि सर्च ट्री में जो लोएस्ट लेवल पे जो आ सकता है, दिस इज लेवल 0, दिस वाज 1 2 एंड दिस वाज लेवल m, जो मैक्सिमम लेंथ हो, मैक्सिमम लेवल जो जनरेट हो सकती है सर्च ट्री में, दैट वाज m. तो अगर m ही इनफाइनाइट है, दैट मीन्स कि कोई देयर वाज सम space like this was the our search space where there was this path which was infinite nodes. There might be some such problems, some problems which has the path like this. So and अगर we talk about कि DFS क्या करता है, it will simply pick one path and go along that path until there is no path left. So अगर path में infinite nodes है and उस path को वो choose कर लेगा DFS, तो it will be in infinite loop forever, right? It will be an infinite loop. That's why if there is such path जो infinite nodes का है, so our DFS might struggle into the finding solution because it might choose that path and go along that path for infinite time. That's why we say कि completeness is there, but only if m is finite, which is generally true as long as it is not specifically mentioned कि m is infinite. तो जब तक किसी प्रॉब्लम में आपको अगर ये गिवन नहीं है कि m might be infinite, you can always assume कि m will be finite. So you can say कि DFS is complete. By default, you can assume m is finite and you can say DFS being complete. So अब DFS to completeness we have talked about. Let's talk about another property called optimality. What about this? Is DFS optimal? And we just saw the example of this. What what the path DFS found? This one, which is definitely not a best path because there are lot better paths are available. And this is not definitely the cost. If you could sum it up, we found that the best path tha, that was this one. So this was the optimal path, right? So DFS is definitely not finding the optimal path. So we can say that DFS is not optimal. So there is no, it is just not like even BFS where BFS was the optimal if there was uniform cost. Here DFS is definitely not optimal at all. What about time complexity? So if we talk about time complexity, then कितने nodes generate हो सकते हैं total? So in the last lecture, I talked about how to calculate this time complexity. So let's go over that. So we have this search. This is the initial state, and then there are b possible actions out of that. Like इससे b possible actions are there, right? And if we go along this, right, it will be something like this. So this was the level 0, this was 1, 2, and let's suppose with this is level T, and if I go along, this is level M. So this is level M. So now what? तो suppose जैसे मान लो I have solution here. There is this one solution, and there is this one solution here. Not exactly here. Let's suppose here. It is also goal node. So there can be multiple goal nodes. So if we see that what DFS will do, DFS will simply start from here. It will go there, then there. It will go along this path until it reaches there, and it will return this solution. So इस solution तक पहुंचने के लिए इसे कितने levels चलने पड़े? M levels. That means कि इसे इतने nodes explore करने पड़ रहे हैं M levels तक. So we talk about कि इस level पे कितने nodes हैं? 1. इस level पे B nodes हैं. इस पे B square, B to the power D, and इस पे B to the power M. So if we talk about total nodes generated by the DFS, which will be B to the power M. So time complexity will be order of B to the power M. What about space complexity? How much space consume हो रहा है? Space किसमें consume हो रहा है? Space is consumed in frontier and visited set or explored set. तो एक बार में कितने nodes store करने पड़ रहे हैं DFS को? Since DFS is what DFS is doing, DFS सबसे पहले क्या होगा? It will store this one, right? So in the initial frontier में this node will be there. After that, this node will be, all these nodes will be there, right? These all nodes will be added into the frontier. Right? Because इसके neighbors है. After that, if I remove this node, तो इस if I remove this one, तो क्या होगा? ये node add होगा. Only, right? Only this one will be added. Or only this one, these bunch of nodes will be added, not these ones, right? Because इन nodes को भी explore भी नहीं किया. तो अगर मैं इसको एक्सप्लोर करता हूँ तो इसके वाले ऐड होंगे सिर्फ. तो इफ आई टॉक अबाउट दिस नोड, तो कौन से ऐड होंगे? सिर्फ दिस वन नोड. तो ओनली इफ यू टॉक अबाउट दिस part of the search tree is being is is, in the, is, in the, frontier. not the rest of the part. So we are simply storing this much nodes, not the every other nodes, not the entire level. So if we can figure out how many nodes are there, we can simplify figure out the time complexity or space complexity of it. And so how many nodes are there? Hmm? But now here also will, yeah, visible nodes only that those will be stored in here. So if we say what if I say the nodes of time complexity of is b into m. That is the space complexity of the DFS is b times m because these are the number of nodes which are being stored in either frontier or explored set. Why this b times m? So let me give a brief overview of this, how this b times m comes. So how many nodes are there? एक node here, एक node here, node here. If we talk about this, there are total m nodes. These are m nodes, right? कोर्स इस पाथ की लेंथ कितने m एंड हर m नोड के पास कितने सक्सेसर्स है b सक्सेसर्स ओनली, जो हम स्टोर कर रहे हैं. तो m नोड्स है एंड b सक्सेसर्स हम स्टोर कर रहे हैं, तो टोटल कितने नोड्स हम स्टोर कर रहे हैं b टाइम्स m. So this is how the space complexity is. So for your exams perspective, you don't have to deeply understand how this space complexity can. You can simply remember this fact that space complexity is this and time complexity is this. For exams perspective, just remember it. You don't have to understand how exactly come, but if someone is interested in how exactly this is being derived, so this is the general intuition behind this. Okay, so with this, let's stop our lecture here. In this lecture, we talk about BFS, how BFS works, DFS, and how DFS works, properties of the DFS, like completeness, which is yes, DFS is complete only if M is finite. Optimality, DFS is not optimal. So DFS might give you an optimal solution sometimes if you are lucky, but we can't always guarantee it. So we don't wanna say it is optimal. Time complexity of the DFS is b to the power n and space complexity of b times n. So if you see that if we compare BFS and DFS for time complexity, so if I simply compare these algorithms, let me simply do this here. BFS and DFS. BFS के लिए टाइम कॉम्प्लेक्सिटी क्या था b to the power d and इसके लिए टाइम कॉम्प्लेक्सिटी was b to the power n टाइम space b to the power d itself to the b times. तो complete, yes, both were complete technically. Optimal, yes, if cost was uniform, if uniform cost. No. So we realize this fact that कि BFS का time DFS has the larger time complexity because M will always be greater than D, greater than equal to D. So DFS has the time complexity greater, but space complexity is larger for BFS because it has exponential space complexity, but where you have the linear or polynomial space compression. So BFS is more time efficient, but DFS is more space efficient. So we and the issue is that this space complexity of BFS is too large. We won't be able, even if we like, this is much bigger issue compared to the time complexity. So though the DFS is usually preferred because of the its less time complexity compared to the completeness is both equal almost, and optimal में यहाँ पे भी BFS and gets the more points compared to the DFS. Okay, so that's it for the today's lecture. We'll talk about another search algorithm called UCS and not UCS. In the next lecture, we'll talk about other search algorithms called depth limited search because of this issue of we realize that there are sometimes this M is infinite, and if this is true, then how can DFS find the solution? So we'll talk about in the next lecture. We'll talk about what happens if M is infinite and how can we solve this kind of problem using DFS itself. So with this, let's end our lecture today.